Share screen. Okay. All right. Now we've seen several kinds of subspaces of Rn. In particular, there was this example. Say you have A, A1, A2, N. These are columns of M by N matrix. Okay, then you have the column space or the range A, which by definition consists of vectors in Rm of the form y equals to ax for some x in Rn. This is a subspace of Rm, and according to the way matrix multiplication works, this consists of vectors of this form: ax1, a1, x2, a2, xn, an, where the x's belong to R. So this is therefore what we call the span of the A's. This is called column space. Okay. Now, we could also write our matrix A in terms of rows. Okay. Certainly. So these A's are rows. Okay. And you can, just like the case for columns, you look at the span of all columns of A. You can also look at the span of all rows of A. Before we do that, let's keep in mind that these rows are vectors in Rn. Okay. And the row space of A row space. The row space doesn't really have a preferred notation, it seems, but it's defined to be just the span of the rows. There are m rows, and it's a subspace of Rn. Okay, we can certainly consider this. Let's look at an example. Okay. Let's consider this matrix. 1, 2, 1, 2, 2, 3, 4, 5, 1, 5, minus 5, minus 1. Okay. So it has this row space being, so the row space of A is the span span of these vectors. Let's keep writing them in the form of a row. Okay. And now you can perform row operations to make A into reduced row echelon form. And in this case, after you actually done the work, we get A we get the reduced row echelon form of A to be this matrix B here. Now it only has 2 non-zero rows. Now the row space of B is going to be the span of the rows of B, but having 0 row, adding a 0 row to the span doesn't do anything. So what you really have as the row space of B is the span of these two vectors. Okay. Now what? Now my claim is that the row space of A, well, as you can see, this is a subspace of R3. The row space of B is also a subspace of R3, and the claim is that these two row spaces are the same space. Okay, and for example, if we are to say that the row space of A is equal to the row space of B, then everything in the row space of A must belong to row space of B. So for example, 1, 2, 1 here is being a vector in row space of A, should be in the row space of B. That is, it has to be written as a linear combination of the two vectors appearing here. Here, oops, here. All right, so we can see that fairly explicitly. 1, 2, 1 is 1, 0, 7 plus 2 times 0, 1 minus 3. You can just check that these two are equal. Well, you can also try the next vector, 2, 3, 5. 2, 3, 5 is in the row space of A, so it should also be in the row space of B if these two are the same spaces. That means 2, 3, 5 should be a linear combination of these two vectors. So 1, 0, 7, well, 0, 1, negative 3. Well, what do? I need a 2 here to make the first entry a 2. I need a 3 here to make the second entry 3. And then the third entry I have 14 minus 9, that's 5. So I'm good. Now, what about 1, 4 minus 5? 1, 4 minus 5 should also be equal to the linear combination of these two vectors. And again, you can just read it. The first entry has to be 1, so that's 1 there. Second entry has to be 4, so that's a 4 there. If you put this combination, you get for the third entry 7 minus 12, that's -5. Finally, for 2 minus 5 and 1, you have 2 5 minus 1, I'm sorry. You have 1 0 7 0 1 minus 3. Well, you need the first entry to be a 2. You need the second entry to be a 5. And that tells you that the third entry is 2 7 14 minus 15. That's -1. So this is telling you that the row space. These are just examples showing that row space is equal to row space of A is equal to row space of B. And remember, the relationship between A and B is that they are row equivalent. And in fact, this is meant to be not only an example of row spaces, but an example of the following general theorem. Okay, which goes as follows. Suppose A is an m by n matrix. Suppose A is row equivalent to another n by n matrix. Say B, then they have the same row space. A and B have the same row spaces. Okay. So you can see that the theorem has the previous example as a special case where you have two matrices that are row equivalent. Keep in mind what this means. Being row equivalent here just means that A and A can be transformed to B via row operations. Okay. All right. So we now consider proving the theorem. Okay. So it's enough to prove that row operations do not change row spaces, right? Because to go from A to B, you perform a sequence of row operations. If each row operation keeps the same row space, then A and B will have the same row space. Okay, so there are 3 row operations to consider. Okay. Now, the first one is exchanging or interchanging the i's and the j's rows. Okay, so suppose your A looks like this. It's written in row form like that. Now, after performing the operation exchanging Ri and Rj, you get a new matrix that takes this form. Okay. Here in this notation, this is the i's row, and this is the j's row. This is the i's row. This is the j's row. Okay. Now let's examine the row space. Oops. Now for A, the row space is just the span of all these A's. So that includes AI and AJ. Now, after exchanging AI and AJ, you still have the same list of row vectors. So it's the same span, just that the list, the order of these vectors change a little bit. So it's very much clear that the two spans are the same. Therefore, interchanging two rows does not change the row space. Okay, so the next operation is I guess KRI. That is multiply the i's row by a scalar k that's not 0. It's important that it is not 0. Okay. Now, again, begin with A, written in row form. Now, if you perform this operation of multiplying the i's row by k, you get the following matrix. Like that. Now we can compare the row space. The row space of A is just the span of all the A's. Now the row space of the new matrix is the span of these vectors. You see the only difference between the list of vectors you use to span is that one is AI, the other is KAI. So let's see here. So if you pick, so you want to argue that these two spans are actually the same. To see that, you just pick an arbitrary element from the row space of A. That's going to look like the following linear combination. C1A1 plus blah, 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 plus CIAI, blah, 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 plus CMAM. Now you can perform the following rearrangement. We've assumed that K is not 0 Therefore, I'm allowed to divide by k. Of course, I can't quite do that without changing the expression. So in order to keep the same expression, what I have to do is, if I divide by k, I should multiply by k. Now, the point is that this is a linear combination of the a's with ai replaced by kai. So that's an element in this new span. Okay. Now, you can also, so this shows what? This shows this an element in the row space of A belongs to the new row space. We can, so to show that these two vectors, these two spaces are the same, we should show that an element in this new row space is also in the original row space, that is the row space of A. So for that purpose, we take an element of the new row space that is of this form. It's a linear combination like these with coefficients d1 through dm. Now you can do the following. Over here, I can combine di and k. That'll give me the following expression. Oops. Instead of di times kai, I have dik times ai. Now, after I rewrite it this way, I get an after I rewrite it this way, I get an expression that's a linear combination of the AIs. So this now belongs to the row space of A. So what this shows is that the row space of the new matrix has any element living in the row space of A. So therefore, the two row spaces are equal. Okay. Now, the last operation we have is this, is to add the k's multiple of the j's row to the i's row. Right, that's the last row operation that we perform. So once again, we want to examine what this does to a row space. To begin with, let's write A again in row form and perform this operation. So that will give us a new matrix whose ith row is changed. AI plus K AJ. Still AJ here. AM. Okay, this is the ith row, j's row. This is the ith row. All right. So once again, what we're gonna do now is to examine the row space. Again, the row space of A is just this span. And the row space of the new matrix is the span of A1 through, well, the ith vector is AI plus Kaj, and other vectors are the same. So again, the question is, are they equal? To check these, we're going to continue, or not continue, we're going to do exactly what we tried to do, what we did before. We're going to pick a random element from, say, the row space of A. Right? That's such a linear combination with coefficients like that. And we will try to write it as a linear combination that looks like it belongs to the new row space. So for that matter, we can proceed as follows. Ci ai plus k aj ej minus ci k aj. You see what's being done here. I add this term, that is ci times kaj. Well, I can't just add it. I have to subtract it as well in order to keep the same expression. So I subtract it here. Okay. That, in doing this, I didn't change the expression, but now I make this expression a linear combination of A1 through AM, except the ith vector I use AI plus Kaj. So that now belongs to here. Okay. Now this. So for the other direction, I should look at a linear combination in the new row space, that is that's like that. Okay. Let's suppose I have an element from this span that's gonna look like this. And what I'm gonna do is to look at this expression and just expand it out. Right, this is DIAI plus DIKAJ. Well, there was also another term containing AJ, that's DJAJ. Okay, and now what I should do is combine the two terms involving AJ. And the result is the following. Okay. And now this is evidently a linear combination of just the A's. Right? So therefore it belongs to the row space of A. So this shows that elements in either span belong to the other span. So the two spans are in fact the same. Okay. This shows, so these discussions that we had shows that the 3 row operations we use keep the row space the same. Therefore, if you perform a sequence of row operations to a matrix, you end up with a new matrix with the same row space. Okay. So now, the next question is sort of motivated by the following goal. Well, the goal is arguably vague. Let's try to describe subspaces. Well, what does this mean? Let's examine what we've done so far. Span, the first kind of subspaces that we had is all these things called span, and they are fairly nicely described, right? Because once you fix these vectors R1s, V1s to VR, you just need these numbers A1 through AR to describe a typical element inside this span, right? And remember, these A's, these A's go by the name of coefficients. Okay, we can certainly consider spans as being sort of reasonably described. Null space or kernel. Okay, so another kind of subspaces that we've studied are null spaces. These are just space of solutions of a matrix system or a linear system AX equal to 0. And we've seen some examples before how to do this, how to describe such a space. Right? To describe an A is to solve the system AX equal to 0. And we know how to do that using row operations. But one thing I want to point out is that in particular, solutions can be described in vector forms. And if you remember how that works, it tells you that solutions take this point x equals to, there's some vector v, there's some number x1, v1, some other number x2, v2, and so on. And what is this? This is, again, telling you that the solutions, hence the null space, can be described as a span. Okay, very well. Now the next kind of subspaces is the range of A. Okay, and this is the span of the columns. This is the column space, more or less by definition. So it's yet again a span. Also, even the whole space Rn itself can be written as a span Okay, because you remember these vectors, E1 being 1, 0 everywhere, E2 being 0, 1, 0 everywhere, namely EI being 0 except for the ith place being 1 for each I. And if you use these vectors, you can easily see that an n-tuple x1 through xn is in the span of these e's. Okay, so well, this looks like, I mean, even the biggest vector space to this date, that is Rn, is a span. So for the purpose of describing subspaces, maybe what we want to try to do in general, that is to describe subspaces as spans. Okay, so let's formalize that so try describe subspaces as spans. So let's formalize that into the following definition. Say W is a subspace, and suppose you have S W1 through Wm a subset. Now we say that S is a spanning set of W if before the if, another way of saying this is that S spans W if every element or every vector little w in W is or can be written as a linear combination of W1 through Wm. Now, in other words, W is the span of W1 through Wr, or Wm, sorry. Okay. Okay, so a spanning set of a subspace is a subset that's so that the span of which is the whole W, the subspace. Okay, so that's just that. That's now we could be interested in some situations like the following. Say example. Let's say you have three vectors. U1, U2, U3. You can ask, does the set U1, U2, U3 span, well, say R3? Okay, that's a valid question. And according to the definition of being a spanning set, what you need to check here is that any vector in R3 is a linear combination of the U's or not. So let's take an arbitrary vector in R3, call it V, say, A, B, C. We need to determine whether whether there exists say x1, x2, x3 in R such that V is x1 u1 plus x2 u2 plus x3 u3. Okay. In other words, we need to determine whether V is a linear combination of the U's, and the coefficients x1 through x3 are considered unknown now. Now this is a linear system with x1, x2, x3 as unknowns. More precisely, the linear system takes this form. In matrix form, it looks like this. Oops. Like that. Right? So we know what we need to do, right? We need to solve the system. So for that matter, let's compute the augmented matrix. It's 1, minus 1, 0, minus 2, 3, 1, 1, 2, and 4. A, B, C. Okay, we can perform row operations. We'll just, at this point, we've seen quite some examples of this kind, so we'll just try to do it quickly. R2 plus R1. Zero here, 1 there, 3 here, B plus A there. Now, what do we do? R1 plus 2R2, R3 minus R2, leaving R2 unchanged. R3 minus R2 is 0, 0, 0, 4 minus 3, 1, C minus B minus A. Okay, R1 plus 2R2, 1 here, 2 minus 2, 2, 0, 2, 7, right, 2, 3, that's 6, plus 1, 7, yes, So 2a plus 2b, 3a plus 2b. Very good. Oops. Yeah. Now next. Now, oops. Two more operations and we are good to go. There's 1 minus 7 R3, R2 minus 3 R3. R3 is unchanged. R2 becomes 0, 1, 0 here. Let's do this carefully. B plus A minus 3 copies of C minus B minus A. And finally, 1 minus 7 R3, 1, 0, 0. 3A plus 2B minus 7 copies of C minus B minus A. Okay. Now, you can now read the answer for x1, x2, and x3. From this, x1 is equal to, well, that 3a plus 2b minus 7c minus b minus a. X2 is b plus a minus 3c minus b minus a, and you can further simplify these two expressions, but that's not what we need to do now. The point is we've succeeded in solving the system, finding the finding the x1, x2, and x3 as coefficients we need. So therefore, for any given vector v, we are able to write it as a linear combination of the u's. So the use u1, u2, u3 span R3. So R3 is equal to the span of u1, u2, u3. Very well. Now, let's take another example. V1, 1, 2, 3. V2, minus 1, 0, minus 7. V3, 2, 7, 0. Again, these are vectors in R3. And the question again is, do they span? And you again formulate on the same setup. That is, you take an arbitrary vector from R3, call it V, and try to find coefficients x1 through x3 so that V is the linear combination of V1 through V3 with coefficients x1 through x3. Okay. Just like the previous example, this gives a linear system, which is 1, 2, 3, minus 1, 0, minus 7, 2, 7, 0, x1, x2, x3, ABC. All right. Very well. So we're gonna, what can we do? We're just gonna have to form the augmented matrix and try to solve the system. And this time I'm gonna skip the details, simply saying that after you do these row operations, you can turn it into reduced row echelon forms, which looks like these. Minus a plus b on 2 minus 7a plus 2b plus c. Okay, now we are ready to try to solve the system, but as always, what you need to do first is to decide whether the system has a solution or not. And for that, you need to look at you need to see if there is a problematic row. In this case, the bottom row can possibly be problematic. That is because it has all the entries 0 except the last one possibly being non-zero. This tells if it's non-zero, then there's no solution. Okay. If minus 7a plus 2b plus c is equal to 0, notice that this is a condition on the vector v, right, that you're describing. If this condition holds, then the solutions are infinite many solutions. The solutions are x1 and x2 are equal to negative 7/2 x3 plus b on 2 and negative 3/2 x3 minus a plus b on 2 respectively. And you can pick the value of x3. In particular, you can take it to be 0. So what does this mean? So this means that for vectors v satisfying this condition here, you have solutions. Therefore, you can write v as a linear combination of the v's, of v1 through v3. If this condition does not hold, then you cannot do that. So therefore, the fact that there is a condition on the vector v for it to be possibly written as a linear combination of v1 through v3 means that v1 through v3 does not span all three. Furthermore, there is a description of the span of these v's. That is, it consists of all vectors a, b, c of this with this condition, minus 7a plus 2b plus c equal to 0. Okay. Okay. Very good. Now let's consider one more example. Right, we've mentioned here when we talk about null space or kernel that if we, what we need to do is, in describing the null space, is to solve the system. And then when we describe the solutions in vector forms, we lead to a way of describing null space as a span. So that should give us a way of finding a spanning set for a given null space. Let's do one example in such a fashion. So we're gonna keep doing this example, it seems. Okay. So this example, in fact, we probably have done this before, but again, we need to, for the null space, just for the null space, what we need to do is to solve for AX equals to 0. And for that matter, what we do was to form the augmented matrix. Let's try to be quick about this. Did we just do it before? Don't remember. It's no, it's not this example, but okay, let's do it anyway. 0 here, 2 minus 2, 0, 1 minus 2, minus 1, 5 minus 6, negative 1, 4 minus 2, 2, 0, 1 minus 1, 0, 2 minus 1, 1. 2 minus 1 is 1. 4 minus 3 is 1. Minus 1 minus 1 minus 2. Now, 1 plus R2, 3 plus R2, R2 multiplied by minus 1. R3 plus R2 will turn R3 into 0 completely. R2 multiplied by minus 1 will just be flipping the signs. And R1 plus R2 would be that. Okay. All right, so this is now in reduced row echelon form, with just leading ones here and there. So that allows us to express the solutions x, which consists of x1, x2, x3, x4 as, well, 2x3 minus 2x3 minus 3x4. Yes, minus x3 plus 2x4, x3 and x4. And we can split this into two terms, one proportional to x3, the other proportional to x4, just like before. Minus 2 x3 minus x3, x3, 0, minus 3x4, 2x4, 0x4. And factoring out x3 and x4 would then tell us the following expression. Yeah. Okay. So this tells us, this gives a general vector description of solutions to AX equal to 0. It's written as a linear combination of two vectors. Therefore, the span, therefore this null space is the span of these two vectors, these two vectors. Okay, very well. So now that we've seen a way of, an idea of thinking about subspaces as spans, with the help of the notion of spanning sets. Now the next question we're going to think about is how to do this efficiently. Okay, but that's our next lecture.